So great. Thank you. Welcome, everybody. I have the nice challenge to present all my 13 slides within 4 minutes. I would like to spend a couple of hours talking about process planning, but I'm not afford to do that. So you can see the title, we're going to talk about systematic approach to process planning. So I think this is really nice because we are in the end, we are the guys who try to realize what the designers have come up to. So we have this connection in these requirements. Let's see if we make this one work. So product is an acronym for process design driven part quality. So it's a collaboration between KTH, Scania, RISE, Volvo and Aurobay, and then Ariadne Engineering and Saab in Linköping. And I have 2 of my partners with me today. So I'm myself, of course, Magnus Lundgren from KTH. I'm a researcher. My research field is process planning, particularly model-based process planning, working a lot with the STEP standards. I think it was interesting to hear you, Rickard. I had a lot of things I would like to say about KIF and AP242, but we don't have time. We take it on the lunch instead. Then I have brought 2 experts here. So I have Mohammad that will tell you about the structured process planning, and then Miroslav that will demonstrate the model-based variation analysis in a process planning context. So of course, the aim of product is like everything we do. We want to strengthen the Swedish production industry. We want to increase the collaboration between industry and academy and also in this field, because I think it's important that we keep our very good industry here in Sweden and we become better and better. We have a couple of more tangible objectives with this project, of which one for this presentation, it's actually related to this improved strategies for part and process measurement and control, and then shorten product introduction. Because if we already know at the design stage using simulation, we have a better prediction of if we're gonna produce this part right or not. So in this project, we have 4 so-called work packages, of which one, the VP one, is probably less of interest because that is only project management. And in this presentation, we're going to focus on this called VP2, Quality Engineering Method Development. And as I said in the beginning, we have 2 other speakers here. I think you can introduce yourself very shortly when it's time for you to speak. And I will give you the fastest introduction to process planning you have heard ever before. Sorry, that was not too fast. Oops, I cannot touch these screens. I have a problem with my fingers, you know, if I come close to this, strange things happen. Okay, so I would say process planning, obvious, it's the link between the design and the manufacturing. We want something in the real world. Somebody specifies its function, and then it's up to the process planner to actually decide how we're going to produce this component. So let's open up this box. And we find inside, there's a lot of things that process planning has to consider. We have to consider, like, not only design the process, we have to consider risks with the process and so on. We have to consider how to verify the process. Luckily, as I said, I have my expert here. He might tell you some more about process planning. This is, I hate this, sorry. So I would just, before I leave over to Mohammad, I would tell, for me, process planning is actually a design process. It's similar to that we design products, but I design processes. So I have an intended state and I have a current state, and my objective is actually to find the way how to manufacture a product. Normally, we don't produce products in one single stage. It happens. In most cases, we have several steps which we produce these products. And so we have called in process parts, we have intermediate stages. We have intended outcome. That is what we have on the drawing. Then we have unintended states. That is what we try to don't happen during that we have risk analysis. Then, of course, we have something called side effects, and that is happening to parts because we use physical processes. So we might get residual stresses or something else as a result of the process, and we have to deal with that. And now I will leave over to you, Mohammad, to explain how we deal with that. So please.
Thank you. My name is Mohammad Haddadzade. I am working as a method engineer at Scania CV in transmission manufacturing. So for sure you will see a lot of gears in my presentation. Okay, let's start with a complex one. We want to see how a process planner thinks when he or she deals with a new product, with a new drawing, with a lot of information. Where should he start, and what features would be the most challenging feature for him or her? Okay, maybe he thinks that a feature with the tightest tolerances would be the challenging one. And when we are talking about the challenges, we mean the manufacturing challenges, the cost point of view, and the time point of view. Or maybe he thinks that a feature that's produced using different references in each operation would be challenging, or a feature that's produced using different tools. The other parameter that's important and will challenge a process planner is heat treatment. Maybe a feature that's affected by heat treatment would be challenging, or a feature with complex geometries, like a 3D geometry. And finally, a feature that's produced in several operations. What would be the most important parameters that a process planner should think about when he is facing with a new drawing? So let's take a look at a feature. We have different definitions for feature, but here in this project, we have defined a feature as a set of surfaces which are used to define a requirement on a part. So for example, on this part, when we have a requirement that defines the diameter of this part, then we have only the cylindrical surface of this part as a feature. And when we see this requirement as a concentricity between these two references, we consider all of them as a feature. So we have defined an index to measure the criticality of a feature, and it includes 8 different parameters. First, for parameters, tolerance sizes, type of tolerance, feature size, and type are affected by design. So we should take them in consideration when we do DFM in an earlier stage of product development. And the others, production complexity, heat treatment effect, machine performance, and tool effect will be affected by process planning. So let's go to check them very fast. The first parameter is tolerance range. We assign smaller values when we have a bigger range for tolerances, and for sure bigger values when we have tighter tolerances. When we have tighter tolerances, we need to spend more time to prepare the machine. We need more often inspection, and it's difficult to maintain the tolerance during the operation. The next parameter is the type of tolerance. It can, when we have dimensional tolerances, we have linear or angular tolerances, and when we face the geometrical tolerances, we have different parameters. Here, you have to assign values based on your part and your experience. For example, when you are producing a thin axisymmetric part, like a ring gear, maybe the circularity would be more challenging for you rather than you produce a box. So we move on to the feature size. We have challenges on both sides. For small features, we require high precision machines to reach tolerances. Tool wear affects a lot, and it's hard to measure. On the other hand, we have some challenges for large features. It requires more power. We need to remove material. So when we think from the cost point of view, it would be more challenging. And the final parameters from design point of view is the feature type. As you have more complex feature, it would be more challenging to produce them. So before we go ahead toward parameters that are affected by process planning, I want to present this concept, reference dependency graph. When we have a part with different references, some of them are independent. It puts on the first level, highest level, and some other references here, like reference C, is defined by references A and B, and finally reference D, that's defined by reference A, B, and C. So we put them in a graph in different levels. And then we have a setup complexity in production. In the best case, you can reach a good result when you are producing a feature and its reference in the same setup and using the same tool. But when you use different tools, or you are producing it in different setups, then you will get worse result. So you have to think about those two at the same time, setup complexity and reference level, to calculate the production complexity. For instance, we have a part with two grooves, exactly the same dimension and shape. So we have the same requirement on those two grooves on the left-hand side and right. But when we check the reference dependency graph, one of them is referred to reference C, that's located in level 2, and the other one is referred to reference D, that's located in the level 3. So we would have more challenges toward the group that's referred to reference D, because it puts in the lowest level. Sorry, yes. The next parameter is the heat treatment effect. If we have hard machining operation after heat treatment, or even though if we don't have any heat treatment on a part, then it has no effect. Otherwise, we have to take it in consideration. For example, when we have this requirement, so our feature is this groove and this surface, and if our setup steps be soft turning of both and then heat treatment and just hard turning of the reference, then we have to assign these parameters in our calculation, because the heat treatment will affect this requirement. And the machine performance is based on your experience, and you have to take it in consideration about accuracy, surface finish, and dimensional stability and production speed. For example, for broaching operation, it's really stable process that you get your good dimensional stability, but the surface finish is not as good as grinding. And the last parameter is tool effect. When you are producing a feature with more than one tool, then you will have more challenges. For example, for this undercut, you are using different tools for roughing, finishing, and profiling. Or maybe you have to use different tools to cut this pocket, this hole. So you calculate this critical index by the production of all of these parameters together. You start with operation planning, then you go ahead, setup planning, which surfaces should be machined in which setup, and you decide about the tool, and finally calculate this critical index. Then if you're happy with that, you go ahead to the next step. Otherwise, you can revise your process steps, tooling, and so on. Because we think that the next step that's assigned tolerances for in-production parts and calculate tolerance chain is really time-consuming, and we need to have a good process steps before we go ahead to the tolerance chain analysis. So I hand over to
step in there quiet before we leaving over to Miroslav. Because yes, so Miroslav will talk about tolerance chains analysis. May I, if I dare to touch this screen. So we have a demo component here. So this is just a fictive component. You can see it's a kind of gearbox things where we probably want these axes to intersect. The problem is how to do this in manufacturing. And I think that all of you know a lot about manufacturing. I think you would say that, yes, of course, if I have a 5-axis machine, let's do it in a 5-axis machine, because then it's just a matter of the machine accuracy. Unfortunately, in this case, this machine was broken, so we had to do it in a 3-axis machine, meaning that we have to split it up in several setups. So now we have a tolerance change. And Miroslav will present that case, how we're using your software to evaluate if the process plan will end up in the right product or not. So please.
Yeah. So my name is Miroslav Shamira, and I'm a founder of Ariadne Engineering, a Westeros-based company specialized in model-based enterprise and dimensional management. We were invited by Magnus to a product project, and our responsibility was to find out a methodology to calculate process-related tolerances. So the target for our participation was to find an easy-to-use and structured method to analyze process tolerances, define what to analyze, and then capture all relevant contributors which may affect quality of manufacturing processes. So the proposed method was, first of all, start with a manual definition of a process. This is done by a human being based on previous experience, cost, and so forth. And then we will do a simulation and verify if this method is good enough. If we have several ideas, of course, we want to compare them and find the best one, with the best quality and most cost effective. We want to identify all contributors and find out critical features and decide if we are good enough or if we have to tighten some tolerances or if we are able to release some of them. And in order to do this analysis, of course, you have to have certain components. The first one is software. And I think CTOL was chosen because of its integration with CAD and also easy of use. We would like to an average, so-called average engineer to be able to use the software and perform this analysis. The second component is geometry. So we modeled all the processes in several steps. And in this case, we had 7 steps. 5 of them were relevant for tolerance analysis. Last 2, it's just material removal from the box, from the cube. So we model all 5 geometries and have them in tolerance analysis system. And then, of course, we need tolerance on part level. And usually, when you do this kind of analysis, tolerances are equivalent to your design specification. But in this case, it was reflecting like capability of your manufacturing equipment. And of course, this specification should be in 3D model and should be semantic and should be readable by machines or by software. And the last component, and this was a real challenge, was to find out process-related tolerances and capture this information. So if we take a closer look at variation, we've got 2 levels. Level 1, we call it for operation variation. So basically, this is tolerance defined on part level, corresponding to your manufacturing hardware. And this is kind of business as usual. Part number 2, clamping variation. So this is tolerance on assembly level, and it's equivalent to variation we will get from fastening processes and so forth. And this part required some methodology. So operational level, you see how it is defined here. We have our ABC reference system, datum systems, and we define tolerances in relationship to the datum system. And as an example, the upper hole position of the upper hole will be broken down to translational degrees of freedom or rotational degrees of freedom, and we can get it into the system and analyze it. Clamping variation, well, first of all, you need some kind of assessment of how big is the variation. We got help from expert, from Magnus, to define that. Then we have to understand how the clamping process looks like, so which surfaces are used and so on. And we are using kinematical methods to model all these things. And I just show you short animation. So the biggest vertical surface can move in translational direction. We can also capture rotational degrees of freedom. So this is rotation of long edge. We will of course capture also the other rotation, and you can graphically see that the short edge gives you more variation. This is more sensitive. Then we have bottom surface, also translation and rotation captured, and finally a point constraint to fasten the detail in the side direction. So this was modeling on the clamping processes. Sorry for that. Now it's time to capture all the geometries. So we modeled 5 steps in the process, and we get into one model. And the challenge here was to find the method to transfer variation from process step 1. So which surfaces will give you variation, which are manufactured and then transferred to step 2, and so forth. If you are interested in details, we can talk about it after the presentation. And lastly, we will measure the function, something which is important for function, in this case, coaxiality. We will get results which can be represented as worst case, the gray bar, show you worst case, and also statistical interpretation. And we will get a contributor list. We'll find the critical features and how much variation is coming from this feature. And of course, we will find the influence on the final results. And we can evaluate it graphically, as you see here. So coaxiality will be affected by misalignment to A. And if we look at the results, so we captured both assembly level variation and part level variation. We divided the major contributors into 3 groups. So clamp rotation was 1 parameter, which gives 56% of variation. Clamp translation, 22. And then the sum of the part level tolerances was 22% of variation. So you can see that the clamping process is very important. We can see animation of variation coming from the clamping. Finally, to summarize that, by having the contributors from both part level and assembly level variation, we could assess the clamping process quality. And as you see, 78% of variation is coming from clamping. So maybe we need some rework and rethinking, changing in the process or tightening tolerances or lowering the variation. And then hardware quality was good enough. We got green light. And that's what was our contribution to the project. So I will give the word to Magnus.
Thank you, Miroslav. So at the very end right now. So this is something new, at least in process planning, because previously or mostly process planning is based on experience, but we don't have these software tools yet to actually evaluate that our plan is working. And I think with this small project within this project, I think we actually have found out that this process would probably be produce a component according to the specification at the end. So we think that we're going to continue to work with this, and I think there is promising future for working with this type of applications in the future. Let's see where we are. So, yes. So I don't know if there are any questions or if we should have like the discussion at the lunch or something, because there's plenty of things here which I connect to each other. Yes, Richard, or yes?
Yeah. Thank you. Very interesting. I haven't followed the process planning for a while, but I looked into in the 90s. There was a hype of computer-aided process planning. I remember there was a system from Technomatics called PART that I was actually looking into quite a lot for a while. And the idea was, of course, to break all this down and find the logical flow. But then I don't know what happened with that hype, or it disappeared from research and lots. So
yes, I would say a lot of research was done in the 90s. So I done the study. I would say it's at least 10,000 different publications in process planning. As you said, it was a hype. I have been working with Technomatics, and I actually consider it's one of the few successful applications. It's quite complex. I as I remember, Technomatic is not really capable of doing this type of verification. It works only on feature level, so you could actually determine if you have a feature tolerance, then you can decide the right process. But then it seems like CAP has become it's not so interesting, or maybe they didn't solve the problem. But I think it's probably a kind of renaissance for
I would think
process.
with AI.
Yeah, I think AI will not. I don't think AI will come up with this type of solution which I present, but I think AI could be a very good supporting tool or work in collaboration with the experts, so it actually could present tips. Think about that, learning. And I think the model-based approach will be very fundamental in that, because we can actually describe our things, and also this specification. That's what I like with the GPS, is like it's really specific. We can describe what we are aiming for.
Thank you.
Yes, a question over there.
This is the last presentation.
We have a question.
Oh, yes, sorry.
Thanks.
Yeah.
Mohammad, thanks for the presentation. Thank you. You have then a space of 8 dimensions, which defines whether or not feature is critical or not. How would you put together these features? Is that one should be in the red zone, or 2 together, or is it the maximum of it, or is it the sum of it, or is it the weighted sum, or yet another aggregation function? How would you, so we say, define then the threshold of something goes to phase 2 events?
I think that a good process plan would be a process plan that you have an even value for critical index for different features. We don't have a threshold that we say, okay, if the critical index is above this value, that would be challenging.
Yeah.
Then we have to compare a part with itself. If it has several features with high critical index, that not will be a good process plan. So we have to revise our process steps.
My suggestion is that AI, especially unsupervised machine learning, could be a supporting component. Thank you.
Yes, I agree with that, because what Mohammad has shown is actually a way to describe what is critical with the process plan. And in the past, like you dealing with the expert, they have tacit knowledge. So you just go and ask them, can we do this? Yes. Can you explain why? No, you have to trust me. So now we have, I would say, a way of actually communicate it. And I think that is more important today when we work in a distributed manner, because like people who want to buy this product or design this product, they don't have to know anything about manufacturing, but we need to communicate with them, explaining why your design is not suitable from a manufacturing point of view.
And the purpose also is bringing this method into the academia.
Yeah.
Make it available, so you can actually perform the analysis and know about it in the learning way. So it's really